Here's an example from an old final exam. And it's really great because we get to practice, let's look at it, critical points, intervals of increasing and decreasing, local max, local min, and then in part D, we are given a closed interval and we're asked about the global extrema. So we get to practice a lot in this problem. It's really great for us. Okay, let's begin with part A. We know the critical points are where, well, they're points in the domain where the derivative is 0 or does not exist. So the first thing we will do is calculate the derivative. We can use the power rule. This is 3x squared plus 6x minus 9. And then, well, this is defined everywhere. So the critical points for this function will just be where the derivative is 0. Let me factor out a 3. We have x squared plus 2x minus 3. And then this factors into, let's see, I believe plus 3 and minus 1. Now let's check. Multiply 3 and minus 1, you get negative 3. If you add 3 and minus 1, we get positive 2. It looks good. Okay, so let's set the derivative to 0. And we get critical points minus 3 and 1. So this is part A. Okay, intervals of increasing and decreasing. Remember, we discussed this in the lecture video. We divide the domain into intervals based on the critical points. So let's begin with a number line. Okay, and then we have two critical points, minus 3 and 1. Immediately, I can write the open intervals underneath. I would have, for instance, minus infinity to minus 3 is one open interval. I would have minus 3 to 1. This is another open interval. And then I would have 1 to infinity. Okay, these are the intervals that come when we divide the domain. Very nice. Now, then we test the derivative because we know when the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. So what I need to do, or what I will typically do, is make a little chart. I will have x, oh, pardon me. I'll have x. I will have, let's see, the derivative factored is 3, x plus 3, x minus 1. And then I will have one more column where I can write here. And all that matters to me is the sign of the derivative, whether it's positive or negative. So let's pick some points in each open interval. Here, for instance, I can use x equals negative 4. Here, the easiest one is 0. And then here, I can use 2. Okay, so let's test. We have minus 4, 0, and 2. And then what I'm going to do, I just look at the sign. It's all factored, so it's kind of fast. 3 is positive. This would be negative and negative. The first derivative is positive. Well, 3 is always positive. This would be positive, negative. First derivative is negative. Finally, for x equals 2, we have positive, 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 positive. Okay, so now maybe in red, I will put this one. I get a, we see it, I have a plus. I have a minus, I have a plus. Okay, this is the sign of the first derivative. And so we can immediately write down, we know this function, the original function is increasing. Everywhere we see plus, which is minus, infinity to -3, and also the interval 1 to infinity. And the function is decreasing everywhere we see a minus, which is just one open interval, -3 to 1. And let's see, in part A, my answer was in black. So I will do this here. Oh, well, let's make this black also. Okay, so far we have part A and part B. Now we need the x coordinates. Oh, okay, where we have a local max and local min. Okay, here we go. C. Well, the good thing is we have all of the work. In fact, the work is here, but I will just recopy it. All we need in C is x coordinates. Okay, wonderful. So we know that you have a local max or a local min. It must occur at the critical points. And so I just use part B, and what does it look like for x equals -3? I will draw a little number line just for this. We found above, well, we can sort of still see it. If here is -3, we found on this side it's plus, on this side it's minus. And so what I do is I just sketch. Okay, what must the function look like? Well, it's increasing, horizontal tangent, decreasing, something like this. This is not that great of a picture, but you get the point. We are increasing and then we are decreasing. What must occur? Well, look at it. We see a local max. So we have a local max at x equals -3. And then we do the exact same thing for the other critical point, which is x equals -1. We draw, again, this is just what we calculated in B. Here is +1, pardon me. At 1, what did we find? If we look above, we found decreasing, then increasing. So decreasing, then increasing, and we can sketch. We are decreasing, horizontal tangent, increasing. Okay, it looks something like this, right around +1. What do we see looking at this picture? We see a local min. So we have a local min at x equals +1. Okay? So far, so good. We have A, B, and C, and these were very much like a problem that we did in the lecture, but it's always good to see more practice. Now, the last one, closed interval. Remember, when we are on a closed interval, all of a sudden, the endpoints are now critical points because technically the derivative is not defined at the endpoints. Okay, so when we're looking for global, okay, global, it does not matter if you're increasing then decreasing or decreasing then increasing, because you could have a lot of local extrema that are not global extrema. What matters for global extrema, for global max, you want the highest overall y value. And for global min, you want the lowest overall y value. Okay? And on a closed interval with a continuous function, we know these must both exist. So what we want to do is we make a chart where we have x, and then, let's see, I'll do it this way. we have the original function, f of x. This is y value. Okay? And what x values do we put in the chart? Well, we put all the critical points. So I see two of them here, -3, 1, and then I need to add, as I mentioned, when we are on a closed interval, the endpoints are critical points, so I will add -5 and 4. Okay? And then this is y value. Okay? So once I make this chart, all I need to do is look in this column, and the highest, largest number that I see will be the global max, and the smallest number that I see will be global min. Okay, so let me recopy the function, and now let us calculate. All we need to do is evaluate the function at these 4 points, which is, well, it's much easier with a calculator, but it's fine. We will make it through just doing it by hand. The easiest one is at 1. We get 1 plus 3 minus 9 plus 5. This is 9 minus 9. The function is 0. So I can write this here. And then at -3, this is minus 27. And then we have plus 27. And then, it's going to be another plus 27 plus 5. We have, the function is 32. Okay, so here y equals 32. F of -5, we have negative 125 plus, let's see, 75. And then it's going to be a plus 45 plus 5. Okay, let's see, what do we have here? That is 80, 120. Oh, we get 0. 0. And finally, f of 4 is, we have 64 plus, we have 48 minus 36 plus 5. This gives me, let's see, 117 minus 36, which is 81. Okay, 81. Now, we pick the highest overall y value. Okay, I'll get my highlighter. It's here. This is the global max for the function on the interval -5 to 4, closed interval. And then, now we look at the lowest. Well, we have it 2 places. Okay, here and here. So now, let's go back and read the problem. We need both the x-coordinates and the f, the y values at those points. Okay, so let's see, I'm running out of space. I will make this a little smaller. Okay, we have a global min of y equals 0, and it occurs 2 places. 1 minus 5, and we have a global max of 81, and it occurs at x equals 4. Okay, so this is the end of part D.